Let's now talk about the components of the vector. What makes up our vector? To do that, we need to introduce this idea of what's called a unit vector. As the name suggests, it's simply a vector whose magnitude is 1. It's a unit. So a unit vector. Every non-zero vector, so remember the zero vector has no magnitude, but it will have a corresponding unit vector in the same direction. You would just multiply it by some scalar, so the magnitude ends up being 1. The notation for the unit vector is the vector we're talking about, that it's in the same direction of, but we put a caret on top. So that is the unit vector. It would end up being the original vector divided by its magnitude, because that would then give it a magnitude of 1. So the magnitude of the unit vector is always 1. Now there's two very special unit vectors that we deal with. It's very useful to break a vector into components that are at 90 degrees to each other. This becomes very, very useful. Now, it's very convenient to make those things at 90 degrees, one horizontal and one vertical. So we're so used to seeing things horizontally and vertically. The one in the horizontal we tend to call I. The vector OI starts at the origin, goes to the right, so it's I. That is a unit. But you'll notice I haven't put the caret on the top, because it's understood that I is the unit vector. The vertical one we then call J. So it's I and J. So the component form of any position vector is joined to the origin because it's a position vector rather than the displacement vector. It'll end up at the point XY. I'm calling it the vector U. So U, the position vector, OP. Its coordinates, or its ordered pair, is XY. Personally, I don't think it's a great way of writing a vector, because you can get confused between, am I talking about the point or am I talking about the vector? So I would steer clear of using that notation for vectors. But you might see it, but I don't think it's great. If you want to write it as a pair of numbers, a column vector is a much better way of doing it, because then it's clear that we're talking about the vector, not the point, the column vector. Or you can break it up and actually write it in component form. And we say, well, it's going x, whatever the distance x is, in the I direction, the horizontal direction, and then we're going y, whatever length y is, in the j direction. That's what we call component form. The magnitude of the vector then, it's like saying, what's the distance of the point to the origin? So it's square root of x squared plus y squared, bit of Pythagoras, or distance formula, whatever you prefer. And the direction, theta, better trick. That'll be the inverse tan of y over x. We can work out that angle or the direction that it's heading in. Equal vectors have the same magnitude and direction. So okay, there's the position vector, but I could move it down there. It's still the same vector. It's now a displacement vector rather than a position vector, but it's the same vector. Or I could have put it up there. It doesn't matter where I put it. And this is the beauty of vectors. We can move vectors around, but it's always the same number, no matter where we put it. To calculate the position vector of any displacement vector, head minus tail would tell us, well, if we were to move this to the origin, where would it end up? Head minus tail will always give us the answer. So let's say AB, the head is 3, 0, and the tail is 0, negative 4. Then I know AB, let's play around with that, is the vector 3, 4. That particular one, 3, 4. CD, it's parallel to it, and I've given it some coordinates there. You'll notice head minus tail also gives me 3, 4. It's the same vector. So if I was to move it to the origin, then P must have been the point, 3, 4. That's where it would end up. Head minus tail will always give us the same vector for equal vectors. In component form, P would be 3i plus 4j. The unit vector in that direction, I would divide it by its magnitude. The magnitude of that one is 5, so it would be 3/5 I plus 4/5 j. There's our second bit.